So in this video, we're going to briefly explain the Solar Nebula model for the origin of our solar system. This is a figure from a paper by Maruyama and Ebisuzaki that was published in 2017 in Geoscience Frontiers. And what they're showing in this panel here, by the way this is oriented is that we're going forwards in time as we move downwards in the graph. So this is time progressing forward as we go down. So this is the earliest stage up here, and they're showing a cloud of dust and gas that's surrounding the sun. This cloud is not randomly distributed. This green area up here above and below the sun is empty space. And so this is a point where a very large cloud is collapsed into a rotating disk, and so they're showing this disk phase in here. But this cloud in this early phase is very nebulous. There are not any particles in it. It's mostly just very fine particles of dust and gas, but no large metallic or rocky grains. But as we move forward in time, in the outer reaches of the disk, what they're showing out here in blue is that some ices begin to form. So this cloud cools, and it cools enough so things like water and CO2 and methane can start forming ice crystals, and they'll do so way out here at the furthest reaches of the solar system, closer into the sun where it's a little bit hotter. We won't have any icy dust, but we will have rocky particles. So we might have metallic iron or various kinds of compounds that involve titanium and aluminum and calcium and silicon, often combined with oxygen. And there are lots and lots of different kinds of compounds that can form out of this gaseous disk, and these are the rocky particles, aluminum oxide, titanium oxide, maybe silicon carbide, various kinds of compounds that will be these rocky particles that will form a little bit closer in where it's too hot to form the icy particles. Of course, those rocky particles, if they can form here, they can form out here as well. So this would not just be icy dust, it should be rocky particles as well. But when we come closer in, those icy particles would evaporate, whereas those rocky particles would not. As the entire system cools, we move down to this level here. So this is T1, the earliest time. This is T2. Now here's T3 at some later time. Those rocky particles are beginning to coagulate to form larger bodies that are called planetesimals. A planetesimal is quite literally just a building block. So we'll write that it is a building block for a planet. They are tiny planets, not really planets in and of themselves. And our model for a modern day analog would be the chondritic meteorites. We'll just call them chondrites. Chondritic meteorites would be our model for what the rocky planetesimals would look like. Out here, if we're in the colder regions further from the sun, those rocky planetesimals will also be intermixed with icy planetesimals. So larger and larger bodies, all of this ice and dust through mutual gravitational attraction has formed larger bodies that we call planetesimals. The easiest way to think about these are as meteorites, though technically a lot of meteorites are not quite the same. They're differentiated, broken up planets that we'll talk about in a later video. So what do these planetesimals do? They coagulate to form larger bodies that we call planets. So here is the Earth and Mercury, Mars, etc., Jupiter, Saturn, Uranus. And as these bodies get larger and larger, they're still showing in blue here a bunch of gas and dust. But as these bodies get larger enough, their gravity is great enough that they could sweep up all that dust. And so here we see these same planets, but now surrounded by green. Remember what we said, the green is just empty space, space that is more or less devoid, not completely devoid of matter, but mostly devoid of matter. So all of this blue and white and gray stuff here has all been accreted onto these planets. So we've gone from a gray nebulous disk out here into discrete planetary bodies, the rocky planets that are in the inner part of the solar system, and then the gas giants and the icy material that's out here in the colder regions of the solar system. If we go even further out, we'll just end here talking about something called the Kuiper belt. The Kuiper belt is a belt of very cold gas and dust. It would be the icy planetesimals that formed out here, but there wasn't enough mutual gravitational attraction to cause them to form very large planets. So they create small things like Pluto. If you're wondering why Pluto is no longer considered a planet, it's because if Pluto's a planet, well, there are dozens or hundreds or maybe even thousands of these objects that are similar to size to Pluto, and maybe even larger than Pluto, that are out here. So if Pluto is a planet, then there are literally hundreds or maybe even thousands of planets, and astronomers decided that it's easier to just consider the inner the inner 8 bodies as planets and to skip the rest. They're not showing all 8 here for some reason. I don't know why. In any case, the Kuiper Belt is not only the source of objects that look like Pluto, it is also the source of comets. So sometimes one of these little icy planetesimals or a small icy planet, we'll call a comet, its orbit will be perturbed, so it'll leave that outer part of the solar system and come very close to the sun, and then rocket its way back out to the Kuiper Belt. And when it makes this close pass to the sun and to Earth, then we see those in the form of comets. So this is the idea behind an early solar nebula that gave us the 8 planets plus Pluto and the Kuiper Belt and comets, etc.